Hello everyone, we are Team 7, representing one of the groups from Professor Lantois' Orbital Mechanics class, Section 2. Starting from left to right, the team consists of Diane Amon, the team lead, then Kedar Zoriker, Atharva Karnik, James Urias, Andrew Rashid, and Daryl Angelis. Today, we will be presenting to you our Ceres sample return mission, which encompasses basic orbital mechanics and mission planning. So the outline of this presentation is as follows. We will first discuss an introduction of why and how we are going to do this mission, which includes the mission requirements. Then, mission overview. Following will be modeling assumptions, then technical calculations and analysis, and finally, our final design and summary of the mission. Ceres is the first dwarf planet to be visited by spacecraft, that being Dawn. With the conclusion of that mission, a new interest is sparked to design a sample return mission. For our mission design, we were tasked to schedule major events of our mission, calculate pertinent values such as delta V's, and trade studies for launch vehicles. Software is primarily used to complete this mission were NASA's JPL's Horizon Web Interface to generate ephemerides, MATLAB to generate porkchop plots and mass calculations, along with FreeFlyer to model trajectories and rendezvous. These are the mission requirements which were stated within the problem statement. The launch must take place between 2025 and 2035, and the total duration of the mission cannot exceed 15 years. The spacecraft cannot travel below 0.6 AU because of thermal concerns. The whole dry mass of the spacecraft is 1,200 kilograms, 300 of which are the lander and 70 of which are the return capsule. We must enter Earth's orbital sphere of influence below 10 kilometers per second. The orbital altitude above Ceres at 50 kilometers and a launch vehicle on the LSP website were also implemented. Now that the requirements have been stated, we can now proceed to assess the mission overview. This simple diagram shows the basic stages of the mission. The spacecraft will first launch from Earth, then rendezvous with Ceres. This will put it in a sun-synchronous polar orbit with an altitude of 50 kilometers. When the lander is directly over the Ocator crater, we will release a lander with a sample collector down to the surface. Once the samples have been collected, the lander will ascend and rendezvous with the orbiter. The base of the lander will then be let go, and the return capsule, pictured to the right, will launch from the orbiter back to Earth with our samples. Now we have the timeline of events. First is the launch from Earth on December 7, 2031. A time jump is made in the timeline, whereby in about 2.5 years, the spacecraft will arrive at Ceres on June 9, 2033. Then, the lander will detach, deorbit, and descend down on July 11th. For almost 19 days, the lander will take samples of the crater at varying depths, with a total of 1 kilogram of sample being collected. On July 30th, 2033, the lander will ascend back and dock with the orbiter above it. On August 4th, 2033, the lander base will detach from the orbiter, and the return capsule will launch from the orbiter. Finally, we will arrive at Earth more than a year later on December 7, 2034, totaling a mission duration of exactly 3 years. So let's see how our mission will play out. Using FreeFlyer, we modeled the interplanetary trajectories to and from Ceres. To the left, we can see that the spacecraft departing from Earth to Ceres. Using the launch date of December 7, 2031, the spacecraft will perform an elliptical transfer to reach Ceres in 2033. As can be seen to the right, the return from Ceres, the spacecraft will use another transfer to get a trajectory back to Earth, leaving in 2033. With the mission now visualized, we can get into technical details. But before going into technical calculations and analysis, some modeling assumptions that were made are listed here. Though Earth and Ceres are not coplanar, for simplicity, we assume so. Parameters and constants are listed hereafter. Continuing on to technical calculations and analysis, this slide presents a summarization of our process in creating our mission. From Horizon's website ephemerides, we can generate porkchop plots for C3 and delta V insertion to Ceres and delta V back to Earth. From the porkchop plots, we are then able to choose optimal C3 and delta V values to insert into Ceres and a delta V value to return to Earth. Delta V's for our descent and ascent mission is obtained, and from there, we can calculate how much propellant is needed. This adds to our mass, which drives our selection for the launch vehicle. And finally, losing the Lambert problem, we are able to model the trajectory on FreeFlyer. The main idea in generating the first porkchop plots is to first take the given launch window of 2025 to 2035 and finding the time between each launch and arrival date. Using the Lambert function to find V1 and V2, we can then find C3, then approach velocity, circular velocity, and the difference between those two to get insertion velocity. Finally, we can plot the last porkchop plot from Ceres to Earth. Here we calculate delta V's between 2030 and 2040 using the Lambert problem to find hyperbolic escape velocity, and then finally the lowest delta V that allows us to return to Earth. On the left is the C3 plot, which allowed us to find the optimal launch dates for our transfers. On the right, you can see a zoomed-in picture of the precise point on our plot we chose. We chose a value of 45.45 for our C3 after comparing it to the porkchop plots of delta V. We generated another porkchop plot to find the delta V needed for the transfer. We compared this with the previous plot and found the optimal C3 that matched up with the delta V we chose of 5.627 kilometers a second. This point on the graph that we chose also gave us our launch date from Earth, December 7, 2031, and our arrival date at Ceres, June 9, 2033. The target landing zone for this mission is the Orbital crater. First, the spacecraft will perform reconnaissance of the landing area. This spacecraft will fly over the Orbital crater between 4 and 8 times a day with a beta angle of 40 degrees. The lander and the capsule will then detach from the spacecraft and descend to the surface on July 10, 2033 in 608 seconds. The lander will spend 19 days on the surface and collect about 1 kilogram of samples. On July 30th, the lander will ascend for 608 seconds before the orbiter is directly above it at 2330. Now, the delta V requirements were determined by finding the x and y components of the velocity. The x component was assumed to be the orbiting speed of the spacecraft, while y component was the speed at which the lander freefalls under Ceres gravity. The sum of these x and y components gives the delta V required to land. It also gives us the delta V required to ascend back to the orbiting spacecraft, since it is assumed the delta V for landing is the same as the delta V for ascending. Therefore, the delta V required for the lander is just the sum of the landing delta V and the ascension delta V. Finally, this is the Ceres to Earth porkchop plot, which was generated with the condition to re-enter Earth under 10 kilometers a second. As can be seen, our optimal delta V to return is 4.55 kilometers per second, giving us a velocity at Earth around 9 kilometers a second. The departure date will be August 4th, 2033, and the arrival at Earth will be December 7th, 2034. So, a hypergolic bipropellant was selected for the orbiter and return capsule since it will be conducting large delta V burns. A total mass of 3,557 kilos are needed for the mission. Hydrazine monopropellant was selected for the lander to reduce lander complexity. The total of the mass propellant for the entire spacecraft is 3,717 kilograms. Here is the delta V requirements for the mission, as well as the required propellant masses we calculated. Arriving at Ceres requires a delta V of 5.627 kilometers a second. The lander requires several delta V burns, totaling 1.042 kilometers a second to land at the Orbital and return to the orbiting spacecraft. Leaving Ceres back to Earth requires a delta V of 4.55 kilometers a second for the return capsule. The total delta V required for the mission for each of the segments of the spacecraft is 11.2 kilometers a second. Each of the mission segment required its own propellant mass calculation due to the changing weights and ISPs, but the total propellant mass is 3,717. Here are the important velocities with relation to specific times during the mission. Mass does not change during the departure from Earth and the hyperbolic approach to Ceres because we assumed the burn to be almost instantaneous at the surface of Earth. No burn is conducted. An insertion burn is conducted, which reduces the overall mass while orbiting Ceres. The lander is ditched after the rendezvous with the orbiter, and the spacecraft is ditched after the hyperbolic escape, leaving just the capsule. The capsule will enter Earth's atmosphere and land in a body of water. 3 candidates were chosen as possible launch vehicles. The 3 vehicles are the Falcon Heavy Expendable, the Delta IV Heavy, and the Alice V. As can be seen, the Falcon Heavy has amazing costs and a deliverable mass at our selected C3 of 45.45 kilometers per second squared. The Delta IV Heavy has an expensive build cost and will only get about 4,100 kilograms of payload up. However, it has a stellar track record for launches. Finally, the Alice V has a very low cost to build. However, it can barely lift even half the mass we need to launch to Ceres. So, using the C3 that was previously calculated, the rockets can be compared by their deliverable mass. The plot shown here was obtained by NASA's Launch Vehicle Performance website. It can be seen here that the Falcon Heavy has the greatest C3 curve out of the 3. The launch vehicle that was selected was the Falcon Heavy Expendable. The Falcon Heavy Expendable offers a payload capacity that meets our requirements while being affordably priced. These are the parameters of the Falcon Heavy launch vehicle in detail, and the most important of these was the ability to launch our mass at our selected C3. For our final mission design, as stated before, the Falcon Heavy was selected to deliver our 5,077 kilogram spacecraft to Ceres. This spacecraft consists of a lander, return module, and orbiter, along with its fuel, pictured to the right. The lander will collect a 1 kilogram sample from Ceres. The entire mission will take 3 years and 1 day, and will cost a total delta V of 11.2 kilometers per second. Now we will look at our requirements to see if they have been accomplished. The launch is in 2031 and has a duration of 3 years. The dates for major events were given. The insertion was indeed a polar sun-synchronous orbit of 50 kilometers. We had a lander reach the equator, collect samples, and come back up to our orbiter. We obtained the total fuel and dry weight so that a Falcon Heavy could be selected for our launch vehicle. And finally, our spacecraft never comes within 0.6 AU of the Sun, so we have successfully created our mission to meet the system requirements. The following slides contain our appendices and list references. Thank you for listening to our mission.